Here we have a problem where we try to identify whether the climber is actually in equilibrium or not. Okay, so the first question is state the conditions necessary for the climber to be in equilibrium. There are only two conditions that you need to fulfill in order for you to be considered as in equilibrium. The first one is that your net force should be equal to zero. Net force equals to zero. And the second one is that your net moment should be also be equal to zero. If either of the two is not fulfilled, then you are not considered to be equilibrium, even if it seems that you are in equilibrium. Okay? All right. The next problem is that you need to complete the vector triangle to represent the forces acting on the climber. So there are actually multiple forces that's acting on the climber. You have your tension force from the ropes, you have your resistive force from the wall, and you have your weight. So we only have here the weight. So what are the forces that actually makes the climber in equilibrium or net force equals to zero? So the first thing is that since the weight is the one that is prevalent here, what is the force that counters the weight? That's actually the force coming from the rope that is vertical to it. So remember, this the tension is actually at an angle which is what 18 degrees, right? Okay, 18 degrees from the wall. So let's say this one, 18 degrees, right? But there is a vertical component of this tension that is acting directly opposite to the weight. So that's Ty. That is equal to that. At the same time, okay, at the same time, I'll just draw it here. Um, the wall is exerting a resistive force, which is R. That is compensated by the force that is vertical, that is horizontal from the tension wire, which is considered as Tx. So we put it this way technically. Uh, Ty is equals to the weight, and Tx is equals to the R. That makes them zero net force. Okay, and the last problem now that we have here is this: the tension T in the rope and the reaction force R. We want to find out what is the tension T in the rope and the reaction force R. I try to snip it or snip the photo here so that we have a reference, so to speak. Okay, so we want to find out this and we want to find out this one. As of this moment, we only know that W, okay, W is equals to, what's the value? 520 newtons. 520. Okay, how are we going to solve this? All right, so in order for us to solve this, you need to understand what are the forces equal to the weight because that's the only thing that we have concrete here. So if you look at your values, remember that the tension wire has also a vertical component, right? Or let's just use, let's say here, so it's easier for us. Okay, so if that is 18, this one is also 18, right? Okay, so if we want to find out this one, because this side here, this side here is actually the one equal to the weight. So is it safe to say, or is it correct to say that t, technically this is cosine, right? T cosine theta is equals to the weight? And the answer is yes. So therefore, t cosine theta equals to weight. We're trying to look for just the t. So we say t equals to w over cosine theta. That gives you 520 all over cosine 18. Answer is 546.8. 546.8. Okay, now let's try to find out R. How are we going to solve for R? Remember that R is actually now equal to Tx here. this line here. And how do we solve this? Tx is multiplied by sine theta. This is opposite side, right? Sine theta equals to r. We know what's t, so we can solve for r. So that gives you r equals to 546.8 multiplied by sine 18. 546.8 multiplied by sine 18, you get 168 or 169 newtons. That's how you solve problems in equilibrium forces.